Hey guys, how's it going? Sorry I couldn't be with you live today, but there's something wrong, as my third block would tell you, with the audio. That was going wrong last week, and I can't figure it out on Zoom. So I'm doing this video for you. It's going to be kind of short and sweet, but following it, you're going to have a project that the rubric is already listed on Google Classroom, and you're going to have 2 weeks to do it. You're going to have until May 22nd. So just to go over a few basic things about what's going to be about. It's going to be about motion, and it's going to be and have to do with Newton's laws. So think about where you're sitting right now. That's your position. But how would you describe it? I'm sitting at a table. I'm on the 9th floor. I am looking, or I am west of the ocean. You might say who you're sitting next to, who you're sitting beside. If you're sitting on a couch, if you're north of something, south of something, that's your position. But all those things that you referenced as where you are near, whether you're north of it, south of it, or something else, is called your reference point. Your reference point is the point or the spot that you're comparing your position to. That being said, let's look at Newton's laws. Newton's first law states an object in motion stays at motion unless acted upon by a force. Think about this. You're playing kickball. The ball's not going to move unless somebody rolls it or pitches it. And it's going to keep going until the person either catches it or it stops somewhere, or you kick the ball back. But if nobody was there and all you did was roll the ball, what would happen? Well, if there was nothing acted upon that ball, if it was in space where there's nothing, the ball would go on and on and on forever. But on Earth, you're rolling it across the ground. The ground slows it down by something called friction. Now, even if you were playing baseball and you toss that baseball through the air has a certain amount of friction. Think about it. You like to run? Run into the wind. I'll bet it slows you down. That's a force. So that's an object staying in motion would stay in motion unless acted upon by some force. Think about volleyball. You toss the ball in the air, you hit it. If it was in space, the ball would keep going on and on and on forever. But it doesn't, because here on Earth, there's friction in the air, and there's also your opponent on the other side of that net, and she or he wants to hit it back at you. And that's that other force that's acting on it. That is Newton's first law. That's it, completely. He wasn't a rocket scientist. You could have figured that. You already did figure that out. I gotcha. So, now it's Newton's second law. Well, Newton's second law. I just did all that without recording. No, I didn't. I'm back. I am here. I was going to get mad at myself right there. So, Newton's second law. This one's a little more difficult, and it states that the acceleration of an object increases with more force and decreases with more mass. So the acceleration, or the slowing down, or the going faster, that's acceleration. We call it deceleration when it's slowing down, but it's actually acceleration. It goes faster with more force. What does that mean exactly? Well, if I am kicking a kickball and I want to punt it, I just kick it with only a little bit of force. And let's face it, it really doesn't go that far. But if I want to kick a home run, I'm going to run up to that ball and I'm going to kick it as hard as I can. Okay, the acceleration, did it go faster when I kicked it harder? Yes. Did it go slower when I kicked it with less force? Yes. It also went further with more force and did not go as far with less force. Now, there's one other part to his third law, or second law, is that it decreases with more mass. Now, I know all of you are young and pretty strong, but if you went outside and you tried to push your bicycle, you could all push it, and I'll bet you can push it pretty quick. Might want to go outside and try that when it comes time for the video that you're going to be doing for the project, if you decide to do the video anyway. But what's going to happen is you can push the bike pretty quick. Now move aside. And instead of it being that bicycle, now it's your mom or dad's car. Now that has more mass. I'm thinking you cannot push that car at the same speed you can with that bicycle. What's another example we can give of that? Size of an engine. If you put the same size engine in a go-kart that you put in a train, the go-kart's going to go pretty fast. The train, not so much. Because the mass of the train, it's not enough power to get it there. And those are things we figure out, or scientists and engineers use every day as far as figuring out how fast something should go, how far something should go. I mean, we're even talking rockets. With rockets, they do that. So now we're on Newton's third law. Newton's third law